Hello guys, welcome back to another video. In this lesson, we are going to cover how to do the calculations for Gay-Lussac Law, Avogadros Law, and Dalton's Law of partial pressures. Let's begin with Gay-Lussac. We have discussed in previous lessons that Gay-Lussac is going to represent the relationship between temperature and pressure, which is going to be direct. Here we are assuming that the constants are remaining the same, so that would be our number of moles and volume. Now, it is important that we understand why the pressure is increasing. Well, think about it this way. Temperature is the average kinetic energy. So if the average kinetic energy of particles is increasing, meaning they're moving faster, they have more energy to travel, correct? Then they are going to have more collisions. Now, within those collisions, some of those will be towards the sides and the walls of the container. And that is the definition of pressure. So the higher the temperature, the more the average kinetic energy would be of the particles, the more collisions they have, and therefore the pressure increases. So let's look at one example for Gay-Lussac's law. The question states, what is the pressure inside a 0.250 liter can of deodorant that starts at 25 degrees Celsius in 1.24 atmospheres if the temperature is raised to 110 degrees Celsius? Now, it is important here to note that yes, pressure was mentioned. We have some volume in there as well, and we have temperature in there as well. But because we're looking at Gay-Lussac, and we're also not really changing the volume, we can assume then that the volume itself is going to remain constant. So this information right here can be ignored because, again, the can did not change size, so the volume remained the same. Now, as in our previous lessons, we learned that for any degree Celsius, we have to convert that into Kelvin. So anytime that we see that degree Celsius, we need to change it. And there was another one right here. So we need to add, for both of them, 25 plus 273, which is going to give us 298. And then 273, and then the 110, which add those two numbers, and that would give us 383. So whenever we write down our numbers to the equation, those are the values that we need to use, not Celsius. Now, I'm not going to label in this particular example all of the different variables, simply because we have been doing that in previous lessons. But for this one, we are going to have our initial and our final pressures and temperatures. So we are told that it starts with 298 Kelvin. So that would be right here at the bottom, 298. Now for the volume that was for the pressure that was initial, that is 1.24. And then we are told that the temperature is raised to 383. And we are being asked for what would the pressure be. So we are looking for P2, final pressure. And just like before, we are going to cross multiply. So we are going to do 383 times 1.24. We're going to divide that answer by 298. So my final answer for pressure, so P2, equals 1.593. Now, it is important that when we write our answers, we do have the information for the units. And I know that it's atmospheres because we started with atmospheres. Now, just as before in our lessons, just always double check. You know that Gay-Lussac's law is direct. So let's look at what happened to the temperature. The temperature went from 298 to 383. So that means that the temperature increased. So we would expect the pressure to also increase. And let's look at our values. We started at 1.24, we ended at 1.593. So that would be true. And that's just a quick way of checking that your answers are correct. If for some reason it was that the pressure decreased, then you know that the calculation that we completed was wrong. Let's move on to Avogadros Law. Now, just like the other laws, we established that Avogadros Law has a direct relationship between moles and volume. And that makes sense. If we are keeping the temperature and the pressure constant, meaning the gas particles are not, they don't have a higher kinetic energy, so they're not moving any faster or any slower. And they are also not applying any more or less pressure onto the container. So they're not moving faster, they're not moving slower, and yet they're still hitting the walls of the container with the same pressure. Then if we continue to add more and more and more particles, then in order to take care of the temperature and the pressure to not change, we have to modify the volume. So the more particles, the higher the volume has to be, the greater, because we cannot have an increase in pressure or an increase in temperature or vice versa for decreases. So it's going to be a very similar equation, very similar process, and that's the beauty of the gas laws. Once you learn one, you pretty much know all the other. You just have to also remember that Boyle's law is in inverse. So now let's look at an example for Avogadros Law. The question states, if 3.250 moles of argon gas occupies a volume of 100 liters at a particular temperature and pressure, what volume does 14.15 moles of argon occupy under the same conditions? So again, here the question is giving us additional information. We are told that is a specific, right, temperature and pressure, so that's not necessary in our calculation. It doesn't change, does not make an effect on our overall example. So we are told that we are starting with the number of moles at a particular volume, and we are being asked for the new volume. So we're being asked for V2. Then we are also told that after, right, we would have a number of moles, so that would be N2. So just like before, we're going to take our values, put them into the equation. Now, it is important here that we always remember that we're talking about liters. So if for some reason the volume was given in any other unit that is not liters, we would have to make a conversion, just like we have learned in previous lessons for the metric system. Now, let's do this one. We have volume 1, which would be 100. We would then have the number of moles, the initial one, so 3.250. We would have then the volume, number 2, but we don't know what that is. We're being asked to calculate for that. And then we are also given the value for the final amount of moles, so that would be 14.15. Again, we would use cross multiplication. And what we would do in this scenario is going to be to multiply 14.15 times 100 and divide that answer by 3.250. And we would end up with an answer for volume number 2 to be 435.38 liters. And again, just to make sure that we have our correct values, we saw an increase in the number of moles from 3.250 to 14.15. Then we would also expect an increase in the volume. Okay, so now let's look at Dalton's law of partial pressures. Now, the total pressure that is inside of a container is going to be equal to the sum of the partial pressures of each gas. So basically what we're saying is that any given amount of gas is going to have a pressure. Now, what if we were to mix different gases? Well, if you put them all in the same container, then they're all going to add up to give a total pressure. And that is because each of those gases is going to contribute to the gas hitting the walls of the container. So it's a very simple calculation, but it's a really powerful idea. So the equation is just going to be to find the total. We're going to find the initial pressure of one gas, the initial pressure of the second gas, of the third gas, and so forth and so forth. So I have a visual here that if we were to take a total of 3 different gases, one of them being at 2 atmospheres, the other one being at 1 atmosphere, and the other being at 3 atmospheres, then if you were to combine them all into the same container, all that we really have to do is take into the account and think about the fact that we're adding 3 different gases and each of them is applying its own pressure. So all we would have to do here is add. So for this final, it's going to be 6 atmospheres because 2 plus 1 plus 3, it gives us 6. It's a really easy calculation, but again, a really powerful idea. Let's look at an example. What is the total pressure in a balloon filled with air if the pressure of the oxygen is 170 millimeters of mercury torrs and the pressure of nitrogen is 620 millimeters of mercury, also called torrs? So all we have to do is add, right? Because we want to know the total, the P total. We have to add the individuals. So 170, and you don't have to write the units when you're doing the addition, but it's actually good practice to do that. I usually don't because sometimes I run out of space on the screen. So here we would have 170 plus 620. That would give us a total pressure of 790 millimeters of mercury. So that would be our total pressure. And that is Dalton's Law. One more example. A gas mixture containing oxygen, nitrogen, and carbon dioxide has a total pressure of 250. So we are told that the total pressure is 250. If the partial pressure of oxygen is 50, that was oxygen, and the partial pressure of nitrogen is 175, that was nitrogen. What is the partial pressure of carbon dioxide? So that is our question. Well, if we know that the three of them have to add up to 250, what we could do is just do the opposite. So from 250, we could subtract 50 to account for oxygen and then subtract 175 to account for nitrogen. Then we would end up with the value for carbon dioxide, which comes out to be a total of 25 mmHg. So I like to leave Dalton's Law usually until the end because it is the easiest one to calculate for. But it is an important law because it still takes into account the fact that, well, what if we start to mix in together and create mixtures of gases within a container? All right, guys, that is it for this video. In our next lesson, we are going to learn about the combined gas law and also the ideal gas law. Thank you guys so much for watching.